Hi, everyone. Happy Valentine's Day. We'll give people just a minute to join. Yeah, very nice of you all to take some time away from your Valentine to study quantum computing today.
What are you talking about, Rachel? Quantum is the greatest love of all.
Yeah, if you have quantum computing, you don't need a human Valentine.
¿Por qué no los dos? Study quantum computing with the bae.
Yeah. Yeah, invite your Valentine. This can be your Valentine's Day date for today. Oh, man. Alrighty. Oh, go ahead, Fran.
I was just saying, I know no date more romantic than learning some
Lecture.
quantum computing.
Lecture with Fran is my kind of Valentine's Day. Oh, man.
Okay, I will put up the title slide. So before Rachel gets into announcements, I just wanted to say hi, everyone. I know it's been a while since I've had the opportunity to lecture. You had a solid month with Amir learning about quantum mechanics, which is super exciting. And today we're actually going to start a really fun lecture series on quantum computation. So for the kickoff today, we'll be talking about the quantum circuit model, which is kind of the basis of how we'll be thinking about quantum computing. But over the course of the next month or so, we'll be learning how to program quantum computers, the math that goes behind these quantum circuits, and then start actually diving into really cool applications and quantum algorithms. So a lot of fun to look forward to. And I'm glad I'll get to lecture you for that part of it. And then I'll pass it over to Rachel for some announcements.
Perfect. Yes, we expect everyone to fall in love with quantum computing today if you're not already, which is why we scheduled this lecture for today, right, Fran? It was all planned. Okie dokie. Hi, everyone. Happy Valentine's Day again. Just 3 quick announcements from me. So first, we've been saying this since last week, but please take the time to set up your IBM Quantum Experience account if you have not already. The announcements have been posted along with instructions on Canvas twice now. So there's a little guide. It's very easy, but you do have to go in and like confirm your identity or confirm your email address. So please take the time to try that this weekend. You will be using it in lab sections this week. Akshay has designed a really fun lab to work with the circuit composer on IBM Quantum Experience and practice some of the things you've learned or you'll learn in this lecture. So if you don't set up your account, you will have to just watch your TA during lab, and we want you all to be able to interact during the lab section. And lastly, you will need it for your homework assignment. If you experience troubles, please let us know. Though remember, we are Qubit by Qubit staff. We are not IBM staff. And so if it's an issue with the platform, we can only escalate it to IBM's team. Just the last piece on this is Brian, who designs our homework, recorded himself doing the homework assignment, or the circuits at least. So in case you run into issues and can't access the platform, you'll still be able to complete the homework assignment on time. So we don't want it to cause any additional stress. Everyone will get the support that they need. One other thing, so it's hard to believe, but we are at the halfway point of second semester. So this is technically kind of the midterm. We encourage everyone to take a look at your grade in the course and just make sure you are on track to pass. As a reminder, that's 60% or above. So please just make sure you're getting in your homework assignments, you're attending your lab sections. We want to make sure everyone completes the course and is able to get their certificate at the end to affirm that you completed and successfully passed the class. And then just lastly, Fran, if you want to flip the slide. I hope folks have seen already on Qubit by Qubit social media, but if you have not, we are really, really, really proud to be hosting a first of its kind conference about diversity and quantum computing on February 27th. It will run all day. you can come and go as your schedule allows. But as we've said from the beginning, a huge component of our mission at the coding school and with Qubit by Qubit is to ensure the future of quantum computing is diverse and inclusive. And we have incredible experts coming together for a really interesting day of discussions about uh, basically who are the role models in this space today, what needs to happen to ensure that quantum computing can be diverse and inclusive? How do we make opportunities like this one more widely available for anyone who's looking to learn quantum computing? So I'll drop the link in the chat to the conference website, and then please do spread this to your networks and register yourself, and we hope to see you there. And with that, over to Fran for like a really fun lecture.
All right, thanks for all those announcements, Rachel. So before we get into actual lab content, I just wanted to continue with the Valentine's Day theme. Lots of love from all of the Qubit by Qubit team. And as Rachel said, hopefully you guys have already fallen in love with quantum computing at this point. And I'm super excited for all of the content we'll be covering these next few weeks. So here I actually wrote the term Cubase, and actually since this past week was we had International Women in Science Day, I actually just wanted to tell a fun story from my undergrad and where the term Cubase actually originated. So at MIT, every physics major is required to take the big experimental physics lab course called JLab. And the first day of class, they asked us to find a partner, make a team, and we would sort of do all of our experiments together throughout the class. I partnered up with my next door neighbor in my dorm, Gada, and we deemed ourselves the Cubase because we were two females in the lab, and we were both really excited about quantum computing. Over the course of the semester, we got to do a bunch of really cool, fun projects, working with radioactive sources, doing nuclear magnetic resonance. So in the experimental quantum information processing lessons with Amir, you guys will actually get to learn what the theory of nuclear magnetic resonance is. And then we got to do an experiment with Bernie, the telescope, on sort of astronomical imaging and recreating the curves that led to the discovery of dark matter. But I thought this would be fun just so you guys could see all of the women in physics out there. Our professor, Professor Fakhri, she is one of the leading female physicists at MIT. She does a lot of really cool work on statistical mechanics, and we had a great core staff. So women are everywhere in the field, and hopefully there will be more in the decades to come. My lab partner, Gada, she actually received the Rhodes Scholarship this year, so she'll be joining me in Oxford next year. And it's great to see more women in physics. Okay, so with that, let's jump into the actual lecture content for today. So as I mentioned, we're going to be exploring quantum computation over the next few weeks. So today is our very first lecture on quantum computing. Up until this point, we've been building mathematical foundations. Then Amir introduced you guys to the wacky world of quantum mechanics. And in the very last lecture, he introduced you guys to the block sphere and went a bit more depth into that. And the block sphere, how we represent the qubit, is sort of the starting foundation for quantum information. So thinking about how we can use quantum systems for information processing. In these next few weeks, we'll be building on that a bit further and actually exploring how you can design protocols and algorithms. So today's lecture, focused on the quantum circuit model, will be just a sort of high-level conceptual, more abstract theoretical discussion of what quantum computation is, specifically asking how can we perform quantum computation or perform computation with quantum systems. Next lecture will be really exciting. You should look forward to that. You'll be doing a Qiskit tutorial with a representative from IBM and actually learning how you can program quantum circuits. So again, that's using IBM's Qiskit software. And then in the third lecture, we'll actually take IBM Qiskit and sort of dissect all of the code that they have running behind the scenes and the actual mathematics that goes on behind the scene to represent these quantum circuits we'll talk about today. And then finally, we'll have a series of lectures on introductory quantum protocols and algorithms. So asking how we can leverage quantum for cryptography, teleportation, and algorithms. This will all be super fun. But with that, let's start off with introducing the quantum circuit model. So I'm going to start off today's lecture by just talking about what quantum computing is at a high level, as well as a discussion of how the field emerged and what the motivations were in developing quantum computing. Then we will introduce the quantum circuit model, actually through an analogy to classical computing and Boolean logic that you guys saw actually at the beginning of last semester in Amir's very first lecture on classical computation. There will be a lot of key ideas today. So in my slides, make sure to keep a lookout for these little key symbols. Those will be sort of the really important concepts that I want you guys to grasp. If you get anything out of today's lecture, the key thing that I want you all to remember is that the quantum circuit is a theoretical model for quantum computation, and it has three key components that we're going to dissect over the course of today's lecture, which are states, gates, and measurements. There are a few other key ideas that we will discuss, and a lot of this actually won't be new. You guys have already sort of seen all of these things in different contexts, but we're going to put them all together in thinking about quantum computing as a whole. So our first key idea will be that theoretically our quantum states simply boil down to this form, which you guys all are familiar with now. We had our last lecture on block sphere representation, learning specifically what the different coefficients mean and how to represent a qubit. Our second key idea is that multiple quantum states are represented as quantum bit strings. And we'll think about this in analogy to classical bit strings. Our third key idea is that quantum operations, which mathematically we represent as matrices, are the gates of quantum computation. So similar to how sort of like and or not were the gates in Boolean logic, we'll define what the gates are in quantum logic. And then, unlike deterministic classical measurements, quantum measurements are probabilistic. We've seen this already in the context of quantum mechanics. Now we'll formalize what exactly this means in the realm of computation. And there are some interesting things we have to do with our quantum circuits, which are different from classical circuits in order to deal with this. And then finally, if you want to know the underlying distribution of a quantum state, you need to create the state several times and perform repeated measurements. So that, for example, is one of the key differences between a quantum and classical circuit. But again, these are the high-level ideas. We'll be going into a lot of depth of what those mean over the course of today's lecture. So let's start off by defining quantum computing and also exploring its history. Over the past few weeks, Amir spent a lot of time introducing you guys to a bunch of really fundamental notions from quantum mechanics. You guys talked about wave-particle duality, the Heisenberg uncertainty principle, entanglement, the Schrödinger equation, and the block sphere, all these different components. However, in today's lecture, we're going to move our focus on to actually using these principles of quantum mechanics to perform computation like you would with the computer or phone that you are watching this lecture on right now. So I was trying to think about different ways we could discuss the history of quantum computing. And in looking around, I think actually one of the best sort of histories of quantum computing that also sort of motivates why and how the field emerged comes from this book, Quantum Computation and Quantum Information by Mike Nielsen and Isaac Chuang. So the next few slides are created with different quotes from essentially the introductory section of this textbook. And just as a little side note, this textbook is sort of really foundational in the field. If you walk into any quantum computing researcher's office, you'll probably see a copy of this textbook lying around somewhere. It's a really great book. It's a bit advanced, but the hope is by the end of this class, you guys will be able to then move on and maybe start reading about more advanced concepts in a book like this. So going back to quantum computing, the history of quantum computing actually really starts, I think, in the mid 1900s. And of course, we're still very early on in that history, but this history was two-sided. So quantum computing kind of emerged simultaneously based on developments in two different fields happening at the same time, so in physics and in computer science. So let's start off with physics. What was one of the reasons why quantum computing emerged? So one of the goals of quantum computation and quantum information is actually to develop the tools which sharpen our intuition about quantum mechanics and make its predictions more transparent to human minds. So in Mike and Ike, they actually give a really good example of this, which is that in trying to think about quantum computers and quantum information, there was the discovery of this no cloning theorem, which basically says that while it's easy to clone or copy information, for example, to copy a bit in classical information, it's actually not so easy. It's actually not possible to do that in quantum mechanics. And this was a pretty large breakthrough and actually gave big insight into a lot of questions that people had in physics, specifically about the relationship between quantum mechanics and the theory of relativity. A lot of people in the early 1980s were troubled by the fact that quantum effects could potentially be used to signal faster than light, which of course contradicted Einstein's theory of relativity. So this was the discovery of the no cloning theorem, which was discovered in the 1980s, was one of the earliest results of quantum computation and quantum information. And it gave us sort of a better intuition about how quantum mechanics itself works. Now, at the same time as quantum mechanics was developing as a field, there was growing interest in sort of being able to control experimentally in a lab setting single quantum systems. So in the, for example, early 1970s, 70s, applications of quantum mechanics typically involved control over large quantum systems. So it wasn't possible to go in, for example, and change the state of a single qubit. Usually you could only change the state of, for example, systems of hundreds of qubits. And for example, at the time, a lot of people were interested in high energy particle physics, like at CERN, where they have big superconducting magnets. And that's an example of control over a bulk sample. However, people thought it would be really useful to gain control over single qubit systems. And since the 1970s, people began developing techniques to do so. These include atom traps and scanning tunnel microscopes, which have been really important in different fields far beyond quantum computation. However, it's the ability to control these single quantum systems that allows us to perform quantum computation in a lab setting, right? In order to perform computation, we need to be able to individually control single qubits or maybe 2 qubits, 3 qubits at a time. So precision control over these quantum systems is experimentally kind of what allowed quantum computing to become feasible from an experimental point of view. Now, the motivations that you guys have probably heard for quantum computing actually probably come more from the computer science side. And there's really two key motivations here. The first, which we've mentioned already a few times in this class, is the failure of Moore's law. So it has been seen that Moore's law, which is a predicted exponential growth in the computing power of your computers, is beginning to stagnate because it's becoming increasingly harder to design smaller and smaller transistors, and thus harder to fit more transistors or more bits onto your computer chips each year. And so people are afraid that eventually we might not be able to decrease the size of transistors anymore. People will run out of tricks, and our classical computation power may sort of stagnate. And so by moving to the model or a paradigm of quantum computation, we might actually be able to address this issue of Moore's law and begin a quantum Moore's law where we can increase our computational power by increasing the number of qubits on quantum chips that we have. Now, this is thinking about things from sort of more of a hardware perspective, but it turns out that in addition, by moving to a quantum computing paradigm, we actually can begin to simulate quantum systems and quantum phenomenon within our hardware itself by creating clever quantum algorithms and quantum protocols. Now, there have been results showing that these systems that we can easily simulate on a quantum computer, we can't actually simulate easily on a ordinary classical computer. And actually, this is where the idea of quantum computing supposedly originated. Richard Feynman, who is probably a name you guys have all heard, he originally proposed quantum computers as a way to basically, if you're going to simulate a quantum system, you should simulate it on something quantum rather than trying to code up all of the crazy laws of quantum mechanics into a classical device. And so here on the right, you actually see a diagram of quantum complexity classes. So for those of you who might be familiar with the theoretical computer science field of complexity theory, there are ways of sort of classifying algorithms and problems, their difficulty in terms of computational complexity. And while it hasn't, this is still a very, very active area of research, people believe that the amounts of problem that you can address with quantum computers is larger than with classical computers. And there's a lot of interesting work there. So going more into this notion of complexity theory, many of you might have seen the movie The Enigma featuring Alan Turing, who was played by Benedict Cumberbatch in that movie. And that was the story of Alan Turing, who is credited sort of as the father of computation. He designed what's known as the Turing machine, which is depicted here. And basically, this is a model for computation in which you have a string that, or a little tape that has sort of empty cells in it that you can write in ones or zeros. And you have a little head that moves along this tape. And you can write a program that basically tells it what to do when it reads a certain string. And it can read, write, and move along the tape. And it turns out that this is a universal model for computation. So essentially any computation can be simulated by an infinite tape Turing model or Turing machine. And the Church-Turing thesis actually states that any algorithmic process can be simulated efficiently using a probabilistic Turing machine. Now, in 1985, there was a professor, David Deutsch, who's actually here at Oxford, who asked whether the laws of physics could be used to derive an even stronger version of the Church-Turing thesis. And essentially what he found is that if instead of using a probabilistic Turing machine, you actually use something called a quantum Turing machine, instead of algorithmic processes being simulated efficiently, you can actually use quantum analogs of Turing machines um, to efficiently simulate any arbitrary physical system. So rather than just simulating algorithmic processes, you can efficiently simulate things like molecules and quantum processes, which is pretty cool. And this notion of the quantum Turing machine then, of course, led to the notion of quantum complexity theory and further enforced this idea that quantum computers can provide a benefit to classical computers. Now, I know this was all a bit high level, kind of hand wavy, but going into these topics in more depth could be an entire class on its own. So we're not going to go into a lot of detail in this, but of course, if you guys are interested, I would highly recommend checking out the Mike and Ike textbook, and there are a lot of other great textbooks out there which go into these topics in a lot more depth. But for the course of this class, the kind of key thing you need to know is what quantum computing is. And at a high level, quantum computing is the use of quantum phenomena. So these three phenomena that we've seen several times throughout the class already, superposition, entanglement, and quantum interference, to perform computation, ideally more efficiently than classical computers. So our goal with quantum computers is not just to perform computation on a quantum system, but to leverage these properties of quantum systems, which we can use in our computation to actually do computation more rapidly or better than we can on a standard computer. So with that, we're gonna start trying to define quantum computation and think about it from an abstracted theoretical perspective by comparing it to classical Boolean logic. So what exactly is the quantum circuit model? The quantum circuit is a theoretical model for quantum computation, and it has three key components: states, gates, and measurement. We have our little quantum wrapper boy, since states and gates measure. Thought it might be a nice mnemonic to have in mind. But we're going to sort of break down each of these different components of the quantum circuit model by comparing it to its analog in classical circuits. So in classical circuits, we also had states, gates, and measurement. And there are some similarities, but there's also some differences. So let's start off by discussing states. Now, before we go into quantum states, let's think back to classical computation and discuss why exactly we are so concerned with zeros and ones. At the beginning of last semester, we learned about binary representation and Boolean logic. These, however, are abstractions. Why is it that we actually care about zeros and ones? How does a computer know what a zero and one is? And what do these zeros and ones mean on the physical hardware that our computer uses? So if we look into the hardware of a classical computer, we start off with the computer that you guys all seen use. And if we open up our computer, we see that there is a CPU inside, a chip that runs all of the computation. If your fan starts blowing, it probably means the chip is getting too hot. And so the CPU looks something like this, and usually it's something like an Intel Core processor. You take off the hood, and inside of it, you see that there is a more complex looking chip. And if you were to zoom in onto this chip, you would see that there are a bunch of wires. Zoom in a little further, and zoom in further, you see that those wires are actually connecting transistors which lie next to each other. So each of these individual squares is a representation of what a transistor looks like. These are sort of a feat of chemical and electrical engineering. And every company and chip, the transistors might look different. But for all intents and purposes, You can think of these transistors as being switches. They either allow electric current to pass through or not. So they have an off state and an on state. And our classical computers are powered by millions and billions of these tiny transistors that are connected to each other with wires. So, like I said, a transistor is just a tiny switch and it allows electricity to pass through or not. So, theoretically, we abstract away all of this electricity and all of that just by thinking of things in terms of zeros and ones, on and off. So now what happens when you have a bunch of those bits? Well, when you put those bits or transistors together, you can start to think of groups of them. And when you think of them as groups, you can begin to represent numbers, or for example, if you're using ASCII, you can have them represent letters. But if we're thinking about them as representing numbers, we can create binary representation. So last semester, we learned how to represent numbers in binary and how you can do addition and subtraction and all of those different different operations in binary representation. So for binary representation, we basically just have a bit string, which is a series of these switches that are on or off. And theoretically, this represents a number. But behind the scenes, you have to think of this as sort of a connection of transistors somewhere on your computing device. Now, let's take a look at quantum computation. Whenever you look at those nice pamphlets by IBM or Google, what you usually tend to see for quantum computation is these dilution refrigerators. However, this actually isn't the quantum computer. This is just a really, really large sort of container shell for the quantum chip. The chip is usually much smaller, can fit in the palm of your hand, looks like this. And actually, the qubits lie in a really small part of it that looks like this. The point of the dilution refrigerator for superconducting quantum devices is to bring your system near 0 Kelvin, absolute freezing, because in order to effectively operate your quantum device, it turns out that they need to be super cold. So if we take a closer look at this small part of the quantum chip, we see something that looks a bit like this. And if you were to take one of these individual units, this actually is a qubit. So when we are talking abstractly about the qubit on the block sphere, on an actual physical device, it looks like this. And we won't get into the details of what the different components are. This part here, the little squiggly, is actually what we call a resonator. And that's what allows us to control the main part of the qubit, which is here. I personally in lab always like to call my qubits Q babies because I think they're really cute, and especially when you see them in person, they're really small. So that's kind of fun. So analogously to how bits were sort of the fundamental unit of information processing in a classical computer, qubits are the fundamental units of information processing on a quantum computer. So although current classical computers have millions, if not billions, of transistors, current state-of-the-art quantum computers only have tens of qubits. So some of the largest systems today, the IBM and Google devices, only have roughly 50 functional qubits on them, and even those are kind of noisy. However, the hope is that within our lifetime, we'll be able to see the development of quantum computers and quantum chips that have millions of qubits on them. So now, theoretically, we abstracted bits to be light switches. If we now want to try and theoretically abstract a qubit, so we don't have to think about this complicated physical system, which has a resonator and Josephson junctions and whatnot, we can abstract it as maybe a dial, right? Because we've been saying that qubits can be in a superposition of the ground and excited energy states corresponding to our 0 and 1 states. And so we can kind of turn between 0 and 1. And this corresponds in our theoretical abstraction to our probability of measuring 0 or 1. So in this case, our dial is pointing at 0. So we would expect 100% of the time we were to measure qubits like this, that it would land at 0. But potentially if we were to move it here, we would expect that 50% of the time it would be 0, 50% would be 1. And if we were to move it up here, 100% of the time we would measure 1. So now that we've sort of theoretically abstracted away what a qubit is, we can begin to analogously, in classical computing, we thought of bit strings. Well, in quantum computing, we can define quantum bit strings or qubit strings. And essentially, these are comprised by putting together the states of a bunch of individual qubits. And so mathematically, a quantum bit string is represented by something like this. Not next lecture, but the lecture following, we will be talking about the math behind quantum computation, and we'll actually define this symbol here, which it turns out is a tensor product. But in an alternative representation, you don't actually need to write out these tensor products because it gets a bit tedious. So we represent our quantum bit strings basically just as normal bit strings, but with the little ket symbol around. And so, for example, here, our quantum bit string is representing the number 22 in standard binary representation. So we started off by defining classical bits, looking at them from the hardware perspective, and then thinking about a theoretical abstraction of them as switches. And we saw, right, that classical states can take a value of 0 or 1. Similarly, multiple states of classical bit strings can be represented just as a standard bit string with an order of your classical bits. Now, if we move into the quantum realm, we analogously know that our qubits are not constrained just to take a value of 0 or 1, but can actually simultaneously be 0 or 1. And then, of course, we saw with our discussion of quantum mechanics, right, that as soon as we measure them, we observe our state, it has to collapse to be a classical bit string. But for the purposes of our quantum computer, when we're performing the actual quantum computation, generally we haven't yet observed our quantum state. So we are manipulating a state that is in a superposition. And this is one of the key advantages, really, of quantum computation. We can manipulate the state while it's in a superposition of states, whereas in a classical computer, the whole time we're working with it, it's either 0 or 1. It can't ever be both. And then analogously to quantum bit string, we can define, to classical bit string, we can define a quantum bit string, the key difference being mostly a notational one. We just stick our ket around our bit string. So hopefully most of that was familiar to you guys from last semester and the recent discussions of the Bloch sphere and qubits. With that, we'll transition into a discussion of what gates are in our quantum circuits. So again, before we dive into the quantum realm, let's do a revision of how gates work in classical systems. Specifically, last semester, we learned about how Boolean logic can be used to manipulate classical states. And we actually learned about a few different logic gates in particular. So we talked about and, or, not, and what they do. I just wanted to do a quick practice problem revision of this to get you all back to thinking about Boolean logic. So I'm going to draw out a circuit here and I'll give you guys a few minutes to just do some quick practice and try and think about what the output of this circuit might be. So we have 1, 0, 0. This is an and, this is an or, and this is supposed to be a not. So I'll make a poll and give you guys a few minutes to try and work through this, practice, and mark when you've completed the problem. We'll revise the answers and then continue on. All right, it seems like most of you have answered the problem. So let's just quickly go through and revise our Boolean logic. So our input to this classical circuit is 1 and 0. So 1 and 0, we remember that and only gives an output of 1 if both of the inputs are 1. So we know here that our output value is 0. Now we're putting both of these zeros as an input to an OR, and we know that OR gives 1 as an output if any of the input bits are 1. Since both of our input bits are 0, the output of the OR is actually again a 0. But then, of course, the role of the NOT gate is to perform a bit flip. So in this case, since our input is 0, we get 1 at the output. If our input had been 1, we would have gotten 0. So this was just a quick revision of our Boolean logic. So again, sort of these Boolean logic circuits that we draw are actually theoretical representations of actual hardware, which is running behind the scenes in your computer. So if any of you have played around with breadboards, you might have seen little chips that look like these. And these actually have, again, hardware which was designed by electrical engineers and chemical engineers to perform the operations depending on input currents and things like that. So, for example, in the chip I have here, behind the scenes, it's basically performing an AND. When you input, you connect these wires maybe to different transistors or electrical current inputs, and it'll give you an output on this line. So if you put 2 1s in here, you'll get a 1 there, and so forth. So also, again, remembering our discussion of the stack, we want to remember that all programs that we're writing in Python, in C, in Java, whatever coding language you're using, ultimately, they get compiled down to machine code, which at the end of the day is really kind of performing Boolean logic operations on bit strings. Those bit strings being stored by transistors in your computing device. So in actually drawing out Boolean logic circuits, we're using these theoretical constructs, gate representations, which represent actual hardware and operations that are going on really low level in your computer. And any large program that you write maybe some really complicated machine learning algorithm. At the end of the day, it's being compiled down to a really large amount of just and or and not operations that are being performed on the zeros and ones, which actually lie in your computer chip. And so continuing our theoretical abstraction, each classical logic gate which we actually performs a specific input-output mapping. This is represented by the truth tables that we saw last semester. So in defining each of these operations and or not, we defined a truth table. And so for any classical bit, there's essentially two different possible options. Either the bit stays the same or the bit flips. So here are the 4 total, depending on whether you have a 0 or 1 as input. And essentially what the truth table does for your Boolean logic gate is it tells you for each combination of inputs what the output will be. So just another quick quiz. I want you guys all to tell me what this truth table represents. So I'll give you guys a minute to think about it. Once you think you got the answer, just mark that you've completed the problem in the poll. All right, awesome. It seems like most of you guys think you've got it. So let's just quickly look at the inputs and outputs. So we see that if both of our inputs are 0, we get a 0 out. And this is actually the only combination of inputs for which we get a 0. If we have a 1 as any of our inputs, we get a 1 at output. So which gate does this remind us of? Well, this reminds us of the OR gate, right? If it was an AND gate, we would only get a 1 for this output and 0 for the others. All right, so far we've just been revising our classical logic and classical Boolean logic gates. So now let's transition to thinking about what our quantum logic would be. So in a quantum computer, what are the different operations we can perform on our quantum states? And so throughout the course, we've actually been hinting about this in talking about quantum operations, we've mathematically been representing them as matrices. Now, last lecture, when you guys were talking about the block sphere, Amir specifically introduced to you guys the Pauli operations, which essentially perform rotations around the 3 different axes of the block sphere. So we saw that Pauli X performs a 180-degree rotation about the x-axis, Pauli Y about the y-axis, and Pauli Z around the z-axis. Specifically, Amir also worked through examples showing you that in terms of the state of a qubit, the Pauli X is actually analogous to a bit flip. So if your qubit is in the 0 state, it will take it to the 1 state. If it's in the 1 state, it takes it to the 0 state. If it's in the plus state, it goes to the minus state, and so forth. Whereas Pauli Z is a phase flip. So if your qubit has a relative phase that's positive, it'll make it negative. And if it's negative, it'll make it positive. And then, of course, you can also perform parametrized versions of each of these Paulis, where instead of moving, for example, by 180 degrees, maybe you only rotate by 40 degrees or something like that. And so it turns out that these Pauli operations really are the basis for all single qubit operations that we can perform. So in quantum logic, we will essentially be constructing combinations of these different rotations. And so this slide is a bit more advanced mathematically, but it's really kind of putting together all of the math concepts that you guys learned about last semester. So see if you can follow through with this. If you're still a bit rusty or maybe still trying to piece together all the math from last semester, totally okay if you don't fully understand this slide. It's a bit more advanced, but I thought it might be exciting for all of you. So we talked about how qubits lie in a two-dimensional complex Hilbert space. Remember, Hilbert space is just a vector space with an inner product defined. And this complex Hilbert space is known as the box sphere. So that visual representation you guys saw last week is just a representation of this Hilbert space. So a few lectures ago, or back when we were doing the math lectures, we also showed that the eigenvectors of these Pauli matrices on the previous slide actually form a basis for the quantum complex Hilbert space. So remember, a basis means that essentially we are spanning the whole space. So any matrix, which kind of represents a quantum operation, can be expressed as a linear combination of eigenvectors. Remember, linear combinations are like we gave the example of sort of a fruit salad. You can have 5 strawberries, 3 blueberries, maybe 4 apples, put them all together, and a fruit salad is a linear combination of fruits. Similarly, you can form a linear combination of matrices. So any matrix which represents a quantum operation can be expressed as a linear combination of a Pauli's eigenvectors, or every quantum state is a linear combination of a Pauli's eigenvectors. Furthermore, in quantum mechanics, observable operations, we said, are Hermitian. And remember, that was just a special type of matrix. And it turns out that the Pauli matrices, X, Y, and Z, plus the identity, sometimes the identity is called a Pauli matrix, form a basis that spans the vector space of 2x2 Hermitian matrices. So these are all concepts we learned about last semester. And kind of putting everything together, what we see is that any 2x2 Hermitian matrix corresponding to an observable quantum operator can actually be written as a unique linear combination of the Pauli and identity matrices. Now, this is a super, super cool fundamental fact in identity and quantum information. And essentially what this says is that all observable single qubit operations correspond to rotations in the box sphere. So we saw, right, how the different Pauli matrices correspond to rotations in the box sphere. And since we can create any observable quantum operation by a linear combination of these different Pauli matrices, rotation matrices, basically every quantum operation just boils down to a rotation of your state in the Bloch sphere. So this is really cool for single qubits. And so here we have our first key idea for gates, which is that we can manipulate the state of a single qubit by rotating it in the Bloch sphere. So more generally speaking, quantum operations, or which mathematically we represent as matrices, are the gates of quantum computation. So instead of just having and, or, not, and so forth, we have basically the set of all 2x2 Hermitian matrices as single qubit logic operations, so to say. And you guys have already seen all of the most important single qubit gates. We have our Paulis, which we represent as X, Y, Z. We have our Hadamard, which is an H, and we have our phase gates, S and T. Now, with these gates alone, though, performing rotations on a single qubit, or maybe performing single qubit operations on a collection of qubits, is not really enough to get the advantages we would want to outperform classical computers. In reality, to outperform classical computers, we can't only have superposition, but we also need the other fundamental property of quantum mechanics, which is entanglement. And this actually comes by using multi-qubit logic operations. which are represented by matrices which are larger than 2 by 2. And so these operate on multiple qubits simultaneously. And so here I'm just going to draw for you a few of the few most important 2 by 2 or 2 qubit logic operations, and then the Toffoli is a 3 qubit logic operation. So C naught looks like this. So each of these lines here is a wire representing the state of one of our qubits. And basically the C naught gate has a control bit and a target bit. And essentially what this is telling us, it's a controlled X gate. So basically what it says is dependent on the state of our qubit, which is on this top line here, we may or may not apply an X gate to the qubit which lies on this second line. And this C naught is what we will use to create our entangling circuit, for example, to generate Bell states. I'm getting a bit ahead of myself. We'll be exploring all of this in much more depth in the following 2 lectures. But conceptually, it's very important for you guys to realize that there are larger gates than just single qubit gates. And the key thing to note as well is that these multi-qubit gates can't actually be boiled down into sets of single qubit gates. They're sort of mathematically and fundamentally different. So like I said, the C naught is kind of like a controlled X gate. The role of the swap is basically if you have qubits on 2 different lines and you want to swap their value. So maybe qubit 1 is in state A and qubit 2 is in state B. If you want to set qubit 1 to state B and qubit 2 to state A, you can perform a swap gate between the 2 of them. And that's just equal actually to a series of controlled knots. And again, you guys will be seeing why in the weeks to come. Now, the Toffoli gate is actually a 3 qubit gate, and you can think of it essentially as an extended version of our C naught gate. So whether or not we perform an X gate here is dependent on the value of 2 other qubits. In principle, we could define an n qubit quantum gate. So we could define a 10 qubit quantum gate. We could define an 100 qubit quantum gate. However, in practice, in a lab setting, it's already really, really hard just to get these 2 qubit quantum gates working. And as you increase the size of your quantum gates, it gets harder and harder to implement. So for theoretical purposes, people try and limit it really to these fundamental gates. And Amir actually briefly at the end of last lecture discussed the concept of universality, in which you guys saw that basically any quantum gate can be deconstructed into smaller sets of gates. So specifically, he told you about the universal gate set, which I think is C naught, Hadamard, S and T being our 2 phase gates. However, there are also different sets of universal gate sets. So there's different combinations of 2 and single qubit gates. I think the Toffoli by itself might even be a universal gate. I would have to double check. But yeah, there's all different combos of those. And depending on what your experimental setup is, you might be able to use certain gates, but not others. So with that, we saw what quantum states and quantum gates are. We'll now take a 10-minute break. After that, I'll answer some questions and then we'll discuss quantum measurement and then put everything together to discuss quantum circuits. So with that, it is currently 3 p.m. Eastern time. So I'll say break until 3:10 p.m. EST. All right, see you guys all in 10 minutes. I think Gabby is gonna put up some music for you all during the break, so I'll let her do that. right, everyone. I think it's 3:10 p.m. So we'll start back up the lecture. We got a bunch of great questions throughout the lecture and over the break that Akshay filtered for us. So we'll be answering some of those now. So one sort of question that a lot of people, it seems to be asking, was why do quantum computers need to be so cold? And I want to just start off by saying that actually the need of a quantum computer to be cold is a platform dependent sort of things. So in superconducting quantum computers, you do need your devices to be cold, but for example, in nuclear magnetic resonance, which is actually manipulating the magnetic spins of molecules, those don't need to operate at cold temperatures. In fact, when I played around them with played around with them in my experimental physics lab, we had a nuclear magnetic resonance setup just out in the open at normal room temperature. But generally speaking, when so in the case of nuclear magnetic resonance, you're sort of manipulating the spin of your system and equating that to energy. In the case of superconducting computers, however, the reason why it's so important for those spins to sort of, or for the system to be cold, is because you actually are looking at the energy of your physical system as a representation of the state of your system. So like we said, right, this notion of a qubit where you have a vector rotating around in a Bloch sphere is a really nice visualization, but it's sort of a theoretical abstraction of all the underlying physics. At the end of the day, as you guys saw in your quantum mechanics lecture, these states of a qubit actually correspond to energy levels in your quantum system. So 0, our theoretical abstracted 0 is representing the ground state, and 1 is representing an excited state. Now, in your superconducting quantum computing devices, what you see is if you actually have tried to operate the system at high temperatures, that sort of the energy from the surroundings gets absorbed by your quantum system and excites your qubit to higher energetic states. So there's sort of an energy transfer from the surrounding into your system, so it doesn't really work well. And a lot of people worked on it from sort of a thermodynamics perspective and derived really rigorous physical bounds for the operating temperatures necessary for the specific types of circuits that people use in a superconducting quantum computing lab. And I think they found that if your system is operating something below like 50 millikelvin, you you'll be able to operate your quantum devices. But if you're above 50 millikelvin, there's just so much, I guess, energy from your surrounding system that gets transferred into your quantum device that you are constantly just in an excited state, and it doesn't allow you to actually perform computation. Now, the key thing to note, however, is the closer that you can get to absolute 0 in temperature, right, the less likely it is for energy, unwanted energy from the surroundings to leak into your quantum device. And so energy leakage, unwanted energy leakage into your quantum device is actually a way that noise is introduced in our system. So a lot of you guys were asking about noise and what that means for quantum systems. Well, generally, noise is kind of just like unwanted errors in our states. So if, for example, we're trying to put our qubit into the ground state, maybe to start running our algorithm, but then some unwanted heat from our surroundings is transferred to energy in our quantum device, maybe it'll get excited to the 1 state. And then any computation.
Hey, Fran.
Yeah.
Do you want to turn your camera on? I think it's still off from the break.
Sorry.
No problem. Go ahead.
Hopefully people have been hearing me though, right?
Yeah. Yep. People just want to see you too. All good.
Okay. So sort of any energy from so if we, for example, some energy leaks in, we get excited to, for example, the one state, any computation we perform after that will be inherently wrong because we've just started our algorithm from the wrong state. And error could be introduced at any point of time. And of course, the more complex the algorithm we're trying to run, the more likelihood there's for errors. And so actually I have at the end of this slide deck some slides I prepared talking about the difference between quantum computing and actually analog computing, which was a type of computing that was proposed roughly around the same time as quantum computing, and people thought it would be a lot better than digital computing that we know of today. But it turned out that it just wasn't practical because they couldn't address issues of noise in their system. So hopefully we have time at end of lecture, maybe if you guys can stick around a bit longer and we'll have a discussion on that. But I wanted to let Akshay actually address one of the questions that we got, which was, how do we make transistors so small? And how do you build a computer chip cheaply since it has to have billions of transistors on it?
Yeah, so this is actually a really interesting question, and it's a whole field of study in and of itself, is the how do you fabricate these transistors. And while you guys get lost in the glitz of quantum computing, I want to remind everyone that what is present in our actual current computers is also really, really advanced technology. So the one process I would say which has made all of this nanofabrication, as it's called, possible is this technique of electron beam lithography, which is this idea of using beams of electrons to essentially write circuits. So that is what we use currently to fabricate a lot of these circuits at the very small scale. And the fact that, as you've been seeing in the previous lectures and labs, right, electrons have this really, really small wavelength, that's what allows us to change chips of silicon on those really tiny length scales and make these circuits so small. And it's really interesting because a lot of the same quantum effects that we've been talking about, entanglement and superposition, tunneling, these are all effects that engineers who are trying to make these circuits have to deal with. And these are all sources of noise in classical circuits. So as we make our transistors smaller and smaller, electrons start tunneling from one place to another instead of just moving along classically. And this is a problem because we don't want that to happen in our classical circuits. And so that is, I think, a fundamental difference between classical and quantum circuits, is that in classical circuits, these quantum effects are a problem. And in quantum circuits, they are what make those circuits possible.
Yeah, that's a really great point, Akshay. So what's beneficial for quantum computers is harmful for classical computers. So we'll see over the course of the next few decades how well we can leverage these quantum effects for computational from the experimental end. I think theoretically, quantum computing has a really great foundation at this point. We'll be learning sort of up to what's near state of the art in quantum computation, quantum information theory. But there's still a lot of work to go in experimental quantum information processing before we have devices large enough and resistant enough to noise such that we can actually execute all of these theoretical ideas and algorithms we have at the scale that we want. So with that, we got some great questions about quantum complexity theory, but because I think a lot of people in the audience might not have a complexity theory background, I will leave that as a discussion for later time. Maybe if there's a lot of people in the course interested, we could have like a workshop or something on quantum complexity theory, or do some fun lecture like that at the end of the course. But for now, let's continue with our discussion of quantum circuits and continue with our final component of our quantum circuit model. So we said, remember that quantum circuits are comprised of three main components: states, gates, and measurements. Up until this point, we've looked at states and gates. Now let's see exactly what measurement means for quantum circuits and the quantum circuit model. So last semester, when we discussed Boolean logic circuits and gates, we never really talked about the notion of measurement. And you might be asking, why not? Well, the reason for that is, in reality, if you have, say, your big circuit, I don't know, we can, for example, have the same one we did in our problem. If at the output of this circle, you have a 0, when you perform a measurement on that wire, performing the act of measurement doesn't change anything in a classical circle. We will always get 0 unless there's some sort of error, which has really, really low probability usually in these classical circuits. And same thing for 1. If we measure a 1, if our circuit outputs a 1, we're always going to measure 1. So 100% of the time, maybe plus or minus, not plus, maybe minus some epsilon, really small percentage, we'll always get the right state. If we get any other state, that is an error. It's not a sort of thing that we would desire or want to happen in our circuit. It's kind of like maybe a bug of our setup. So in classical circuits, we don't really need to think too much about the notion of measurements, besides maybe correcting for bad measurements or cases in which our instruments might be faulty. And there's actually a whole field of study dedicated to that alone. That's the field of sort of information theory and error correction. In our quantum circuits, however, we are working inherently with systems which are probabilistic. So we expect from the laws of quantum mechanics, right, that we will get probabilistic outcomes depending on what the state of our qubits are. So last class, Samir discussed the notion of the Bloch sphere in depth. And as you guys have seen many times, right, we have this generic form of the, oh, sorry, that should be 1. Of the state of a qubit, alpha, beta, right? And we remember, right, that the amplitude squared of these different terms, these correspond to the probabilities, right, of measuring 0 or 1. So for example, if we're in an equal superposition of the 0 and 1 states, we expect that 50% of the time we would measure 0, 50% of the time we would measure 1. It's often very rare that actually the output of your quantum algorithm will be in solely a 0 or a 1 state. So in actually performing measurements on quantum circuits where you have multiple qubits and are trying to create a quantum bit string, you have to perform repeated measurements so that you can create a probability distribution, which is indicative of what the underlying quantum state is. And this actually goes back to the notion of quantum state tomography. I think I talked about this a bit last semester when I was talking about my own research, but there's a whole field in quantum computing nowadays, which is focused on trying to efficiently assess, efficiently perform measurements on quantum circuits to determine what your underlying quantum state is. Since when we perform measurement, we only see classical bit strings. And so continuing with this notion of repeated measurement, when we did our probability unit, we had a whole discussion of the law of large numbers, where we saw that basically if you have some inherently probabilistic event, the average of a large number of trials should be close to the expected values and will tend to become closer to the expected value as the number of trials increases. So I gave you guys all a demo on the IBM quantum experience where essentially I created a qubit that was, for example, in the equal superposition state. So it was just like 1 over square root of 2. And then I tried measuring it on an actual IBM quantum device. And we saw that for I don't know, 10 shots or 10 repeats of our measurements, I got that we were in the 0 state maybe 70% of the time. And then in the 1 state, only 30% of the time. But then as you increase your number of shots, say all the way then to, I don't know, 10,000 or something like that, you maybe will see that you have like 50.1% chance of being in 0, and then 49.9% chance of being 1. So in general, if you have to perform a measurement on a quantum system, ideally you will want to sort of create that state, or maybe run your circuit as many times as you can, and then perform repeated measurement so that you can ultimately get a distribution over the possible states. And the more measurements that you can perform, the more representative that distribution is of the underlying probabilistic distribution of your quantum system. And the law of large numbers guarantees that this will converge actually to the true underlying distribution. And so quantum state tomography then is the field of thinking about, okay, well, in an actual lab, right, we can't perform an infinite number of measurements on our system. We have finite time, and ideally we want to perform as few measurements as possible while getting as accurate of a distribution as we can. So quantum state tomography is all about trying to kind of come up with tricks and sort of think about maybe the shape of our distribution and how we can perform measurement efficiently while still fully representing our underlying state. So the key ideas here are that unlike deterministic classical measurements, quantum measurements are inherently probabilistic. Whereas in classical measurements, right, if we have some probabilistic nature, that's more because of error and unwanted artifacts in our system. So another key thing to note is that although you can measure along multiple axes, which was actually demonstrated with the discussion of the Stern-Gerlach experiment in the quantum mechanics unit, usually when we are talking about quantum circuits, quantum information, we set the z-axis as our default measurement or our setup. And this is just kind of to have a common reference frame. So for example, if you apply maybe, if you're in the plus state, that corresponds to 50-50 likelihood. Whereas if you were in the plus state with the x-axis set as your measurement basis, right, then that would correspond to 100% probability of measuring the plus state. And so we use the z-axis because it has that 0-1 basis, which is ideal for our quantum computing purposes. And then finally, if you want to know the underlying distribution of a quantum state, you need to create the state several times and perform repeated measurement. So one key thing here that I want to note, which I think trips a lot of people up, is that is this idea of you need to create the state several times. So it's one thing to say, for example, create the state 0, maybe I apply an X gate, and then I perform a measurement on it, and then I run the whole system again. That is very different than, say, for example, applying, or actually the X gate is not a good example because that just puts us in the 1 state. Maybe I'll say the Hadamard state. So here we're in a plus state, right? And we expect our outcome to be 50-50, 0 or 1. So it's a very different thing to sort of repeat this circuit several times versus if we apply our Hadamard, but then, for example, perform repeated measurements like that. And let's think about why, because this is actually a pretty hard idea, but very, very important to understand why. So again, right here, after we perform our HADMARD, we're in the plus state. And then as soon as we are about to perform this measurement, we have a 50-50 likelihood of being in 0, 1. So let's say I flip my coin and my quantum state collapses to 0 here. Well, now, once we've performed their measurement, right, our state has collapsed to the 0 state. We are 100% in the 0 state. So now, when we perform this measurement infinitely many times, we're basically always guaranteed to get a 0, unless, of course, there's some noise in our system. But ignoring that, theoretically, there's no noise. We will indefinitely measure 0. However, that's not representative, right? Because the output of our circle is a plus, and ideally we want to see that 50-50 probability distribution. So what we do with our quantum circuits is we actually run the full circuit over and over again. So we start from our 0, we apply our HADMARD, we measure, maybe we get a 0. Then we start it all over again, we set our state to 0, apply our HADMARD, measure, maybe the second time we'll get a 1, third time we'll get a 1 again, then we'll get a 0, and over time we'll sort of keep getting different results, and we can piece together a probability distribution. So I just wanted to make that clear. Now we're actually going to go and put everything together to describe a full quantum circuit, and I'll go through this again, and hopefully it'll all make sense. So as I said, we're going to put it all together. Going back to the start of the lecture, right, we said that the quantum circuit is a theoretical model for quantum computation with the 3 components: states, gates, and measurement. How can we put all of these together to create a quantum circuit? Well, we started off the lecture by discussing states, right? And so in a quantum circuit, graphically, our states are just represented as our original qubit state followed by wires. And so these wires will extend out in time, and this kind of just represents the state of the qubit over time. And so depending on which textbook or class you're taking, people will have different conventions for talking about qubits. Some people will say that this is qubit 0, this is qubit 1, this is qubit 2, and this is qubit n. In other textbooks, they'll actually count the other way around. So they'll say, this is qubit 0, this is qubit n, this is qubit n minus 1, this is qubit n minus 2. In reality, it doesn't really matter so long as at the end of the day, you know what your original intention was and you're just consistent in time. Because at the end of the day, right, at the output of our algorithm, we want to create a quantum bit string. And so knowing the order of our bits is important. But there are different conventions that people define. And sort of the last kind of key thing I wanted to note about quantum states and our quantum circuit model representation is that depending on some texts, people might initialize their circuits, for example, maybe instead of 0, this will be a 1. They might call this alpha. They may say this qubit is initialized to a plus state. And in theory land, that is totally fine. It doesn't really matter what you start your circuit in, but actually for experimental purposes, you're depending on what your platform is. In most cases, platforms are initialized to be in the ground state, and usually you access higher energy levels by inputting energy in your system. So you apply gates to excite your quantum states to higher energy levels to access the 1 state and so forth. So when you actually are, for example, to compile a circuit down to run on your quantum computer, if you say, for example, have 1 and plus as your start state, this actually will need to compile down to 0 followed by an X gate, and 0 followed by a HADMARD gate, because we know that here, right, we have a 1, and here we have a plus. In theory, a lot of times people like to just ignore things that aren't sort of relevant for the theory they're doing. But when we actually go into a lab setting, we need to be careful because all of these gates are not only noisy operations, so every gate we run has some probability of introducing noise or error into our system, but it also takes time. And time, it turns out, is a very valuable resource on our quantum computers. We'll discuss this more when we get into the experimental quantum information processing unit, but qubits have lifetimes on the order of milliseconds. Some of the very best qubits in the world have lifetimes on the order of seconds, but it turns out that quantum states, they usually like to decay back to the ground state. They tend to lose energy to their surroundings. Sometimes they can inherit energy from their surrounding. But our quantum, the gates that we run on our quantum states are really, really short. And we would like to hope that our quantum algorithm doesn't use up a lot of gates, because if it takes too long, the state of our qubit might have already decayed by the time we finish the algorithm, and our output will be just absolute garbage, which is sort of not ideal. So I'm getting a bit ahead of myself, but sort of the key thing that I wanted you to know from this slide is that our states correspond sort of to these wires, which will continue throughout our quantum circuit. And they have some initialization at the beginning. So now this next step in our quantum circuit model is the application of gates. And we've been exploring these over the past few weeks through our discussion of the Pauli matrices, Hadamard. I told you guys earlier about the CNOT. And essentially, these quantum logic gates are really where the computation happens in our quantum circuit. They modify the states, they rotate the states in the Bloch sphere. They also, which corresponds to superposition. If you add phases, that enables quantum interference. And if you use 2-qubit, 3-qubit gates, you can get entanglement. And that's really the third quantum property that we want to leverage in quantum computing. And so graphically, we represent all of these gates as follows. So once again, we kind of have our arrow of time. So you should really think of our quantum circuit as being sort of a series of time steps. So for example, in this quantum circuit here, we have 3 qubits, which are all initialized to the 0 state. In our first time step, maybe we'll call this T1. We applied a Hadamard to the first qubit, a Pauli X to our third qubit, and we left our second qubit unchanged. Now, one important thing to note, right, is that if you just have a wire here, that's essentially equivalent to applying an identity, so multiplying by the identity matrix. Just a good thing to note. So once we've applied all of these quantum operations, we can move on to our second time step, T2, in which we apply a CNOT gate between our first and second qubit. Now, in this third time step, we're performing a CNOT between our first and third qubit. Now, one key thing to note about quantum computing is that these operations don't commute usually. So order from left to right really matters. And mathematically, there are ways to sort of shuffle out the order. And in a few lectures, we'll be seeing sort of how you can represent all of these as vector and matrix multiplication. And there's advanced mathematics you can do to figure out how you can swap the order of things or sort of push things later in the circuit. But for all intents and purposes, it's just good for you guys to think, if I see a quantum circuit, I can't just arbitrarily start flipping the order of gates. So I can't necessarily just go and take this Hadamard and maybe move it to the very end of my circuit, because usually that will give a sort of different result. The other sort of key thing that I want to mention is that although this is sort of just an arbitrary circuit, I just picked random gates to put here for the sake of demonstration. The process of designing a quantum circuit, which is actually useful and will allow us to perform computation better than a classical circuit, is a really challenging thing. And this is essentially what all of modern quantum algorithms theory is about. People want to try and design clever ways to get our input states to interfere, entangle, and sort of create superpositions such that at the output we get a sort of meaningful result for the problem we want to solve. So over the next few weeks, as you guys begin designing your quantum circuits, I think in the problem sets to come, the homeworks to come, you guys will see that there are certain small circuits even which correspond to maybe creating a full superposition state versus creating an entangled Bell state and things like that. And then later on, we'll move to see our quantum protocols, quantum algorithms, which enable us to actually solve really interesting problems. And so, as we mentioned before, right, measurement in the quantum circuit model is inherently probabilistic and something we need to be very careful about. So as I described sort of a few slides ago, with a quantum circuit like this, we are sort of inherently assuming that in an experimental setting, we are going to take this circuit and run it maybe 1,000 times, maybe 10,000 times, 20,000 times, depending on the size of the circuit. Of course, the more times we can run it, the better. But we can't run it infinitely many times. And our objective at the end of the day is to create a probability distribution. So let's just imagine that this is some arbitrary circuit, right? And we say there's some probability at the output of measuring 0 and 1 for each of these states. Well, what we see is that for each measurement, right, we'll get either 0 or 1. So imagine that we just run our circuit a single time, and we see that the first qubit lands in 0, the second qubit lands in 1, and the third qubit lands in 0. That will give us the bit string 0, 1, 0. Let's assume that this is Q0, Q1, and Q2. Now, imagine that the second time we run our algorithm, we get 1, 0, 1. That will give us the quantum bit string 1, 0, 1. And it turns out that in this case, there's 2 to the 3 different possible bit strings that we can create. You can try writing out all the different combinations of 1s and 0s and see. There should be 8 total possible ones. Actually, I can go through and write them really quick. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, right? And these correspond to different binary numbers in binary, right? So this in binary would be 0, 1, 2, 3, 4, 5, 6, and 7. And so essentially each of the different possible outputs we could get from our quantum circuit has to be one of these different numbers in binary representation. And what we see is at the end of all of our measurements, essentially our goal is to kind of create a probability distribution in which we have the different possible bit strings. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so forth. And we'll get a probability amplitude for each of these. And so what this is essentially telling us is the likelihood of measuring each of these possible bit string outcomes. So this is probability of quantum string measurement. And so it's only basically through repeated measurement, we'll say maybe at the end we got 0, 1, 0 10 times, we got 1, 0, 0, 1 30 times. And from that, using our knowledge of probability from last semester, we can go and actually calculate out the probability amplitudes for each of the qubit strings. So hopefully that makes sense. And as you guys experiment with the quantum composer of the IBM quantum experience, you guys will see that the outputs will come in terms of probability distributions over all the different possible bit string combinations. So that's sort of really cool, right? Because in classical computing, if you have some outcome at measurement, if you run the circuit multiple times, you're always going to see the same exact outcome, assuming that there's no noise or error in your system. However, with quantum computers, each time we run our circuit, we usually will expect to see a different outcome, assuming that we're in some superposition states in at least one of our qubits. And it's only by repeatedly measuring our circuit that we can actually understand what's going on in our algorithm. Actually, one thing to note is that if you want to design like a really good quantum algorithm, ideally at the output, all of your sort of quantum states will interfere to the point where upon measurement, you will be in 100% likelihood of the target solution. So if you design a really good quantum algorithm, at the end of the day, you won't actually need to perform repeated measurement, but leveraging the principle of quantum interference, you'll kind of say, I want my algorithm to maybe search for a certain quantity or for the position of a certain thing in a database. And if you have a really good quantum algorithm, it'll constructively interfere away all of the sort of positions which are not corresponding to what you're looking for, and it'll only keep the one that you're looking for. And at the outcome, you'll have 100% likelihood in your target solution. You only need to measure your circuit once, and that's it. But that is usually really hard to do, and more often than not, we need to create these sort of probability distributions over outcomes. So just to kind of put everything together, remember, quantum circuit model, we have states, gates, and measurement. And states correspond to the input of our quantum circuit, gates correspond to the actual computation, and measurement is what we use to deduce the output of our computation. So at the beginning of the class, when we defined the notion of an algorithm, right, we said it was kind of like a black box where you have an input which maps to an output. And usually this is our objective in computation, to do some sort of transformation on our input to some desirable output. I wanted to just sort of take another sort of experimental sort of observation or note, which kind of limits our ability to construct quantum circuits. And you guys might run into this when you're playing around with the IBM quantum experience and quantum composer, which is basically that a lot of times on quantum devices, you actually, for example, can't perform, say, 2 qubit gates between qubits which are not like neighboring each other. So for example, on this IBM Q5 Tenerife device, it's pretty likely that you won't be able to run a C0, for example, between this qubit and this qubit. So that means that, for example, when you're constructing your circuit, if, for example, you wanted to perform C0s between two different sets of gates, it could be that Q0 and Q1 are next to each other on the device, and Q2 and Q3 are next to each other on the device. So you can put your C0 between these two gates, and maybe a C0 between these two gates. But maybe it's not possible to put a C0 between these two gates. And so this is more an experimental limitation than anything, but something you might have to be careful about if you're trying to design a really large circuit. And there's actually whole fields of sort of compilation theory that are devoted to figuring out the optimal way to lay out your map your theoretical quantum circuit onto an actual experimental device to avoid these sorts of issues. I don't think we'll be building any super complicated circuits into which this could be a real issue, but just a good thing to keep in mind. And so finally, I just wanted to show sort of a side-by-side of the Boolean logic gates we learned for classical computing last semester versus the quantum circuits that we will now be using as sort of the basis for all of our quantum computing theory. All the algorithms and protocols we'll be discussing later in the course will really take a form that looks like this. And speaking of what's to come in the course, we're going to be going into a lot of really, really cool and sort of foundational quantum algorithms and circuits. So I specifically, in upcoming weeks, will be talking to you guys about Deutsch-Jose, which was sort of the first ever quantum algorithm. And it was really the first time that people sort of showed that you could use a quantum system to do a computation, which could give an advantage over classical systems. It's more of a toy problem though. It's not very useful in practice, but it will be a great introduction to quantum algorithms. Then we'll talk about quantum teleportation. So thinking about how you could teleport quantum information between people in different labs. Later on, Amir will talk about Grover's algorithm, which gives you a quadratic speedup in database search. So database search is actually a really useful problem, and Grover's algorithm is a quantum circuit which makes use of the principle of amplitude damping, which is specifically a form of quantum interference to strategically allow you to sort through a database and leverage all of those nice quantum properties to speed up the problem. And then finally, we'll also be talking about variational quantum eigensolvers and quantum approximate optimization algorithms, which are honestly getting to sort of state-of-the-art cutting-edge research. So this is something that a lot of researchers are currently working on. In fact, Google recently has published a few big papers showing really interesting results with this for fields like quantum chemistry and stuff like that. And this is really useful from the notion of sort of quantum simulation. So thinking about how we can simulate quantum systems on quantum. And so, yeah, these are exciting and things to look forward to in the weeks to come. Thinking ahead just to the next lecture, we'll be having a sort of invited guest lecture from the IBM quantum education team, and they will be giving you all a tutorial on Qiskit. So they'll be showing you how to take all of the sort of theoretical concepts we discussed today, the actual more abstract picture of the quantum circuit model, and really solidifying it by teaching you how to implement everything using the Qiskit programming language. So for the homework assignment corresponding to this lecture, you'll be using the sort of Q composer, which is a drag and drop interface that allows you to build up these circuits. But in next week's lecture, you guys will be learning how to actually use Python to systematically sort of program out these circuits. And that's beneficial in the sense that later on, when you guys are all super advanced masters of quantum algorithms, this will be an efficient way to systematically produce really large, complicated circuits, right? Because it's a bit tedious to have to go by hand and be dragging things into a restricted sort of drag and drop interface. Just a note, though, that although this class is being funded by IBM and we're using the Qiskit sort of programming language, just like in classical computing, how you had several programming languages available, We taught you guys Python last semester, but there's also languages like C++, Java, R, and Julia. In the sort of quantum programming language domain, there are actually different programming languages corresponding to the hardwares of all of the major corporate players in the field. So like I said, we're using Qiskit, but Google has a programming language called Circ. Microsoft has a programming language called Q#, and even the startup Rigetti Computing has programming language called PyQuil, the quantum instruction language. That's just a good thing to keep in mind, and maybe down the line, as you guys explore the field further, you'll want to learn about some of these other languages, which can be run on different hardware platforms. So that's the end of all of sort of the main content I had prepared for today's lecture. If you guys need to drop, you are more than welcome to. That being said, I did prepare some slides on a sort of compare and contrast of sort of analog computing, which was developed around the same time as quantum computing theory was first being fleshed out. And while people were still figuring out how to build actual digital computers, like the ones we use today, and comparing that to quantum computing. So the notion of error correction and all of that. So let me go ahead and skip to that. And I think this should just be a quick like 10-minute thing. So if you're interested, stay tuned. It's a good discussion of like what noise means for quantum computing. So even though in this lecture, I sort of use the analogy of sort of thinking about qubits as dials, the past few weeks, right, we've been actually seeing that mathematically a qubit should be represented as a block sphere. And so one thing you might ask is, well, what's the difference between a dial and a block sphere? At the end of the day, you have something rotating. Superposition, like what's so fancy about that? Like, couldn't I just, instead of having digital bits in my computer, build an analog computer where instead of my voltages being either 0 or 1, they maybe like instead of 0 volt and 1 volt, I'm at 0.5 volts or something like that. And this actually was something that people considered and worked on for a really long time. So this notion of instead of having bits as dials is the notion behind analog computing. And in the early 1900s, this was something that researchers were super excited about. However, by the 1960s, researchers had to give up on the prospect because they were essentially unable to correct for noise. And intuitively, we can think about this, right? If I have a digital bit, which can either be 0 or 1, and it flips, there's an error. Maybe I'm supposed to be in a 0 state, but an error causes my bit to flip to the 1 state. Well, as long as I can detect that error, it's pretty easy to correct for. And even detecting that error, you would imagine is not super hard, right? Because there's only 2 possible states. Whereas in analog computing, if you need to be, for example, at 0.5 volts and some error induced causes your analog computing state to change to 0.51 volts, that's something that's really hard to detect, potentially really hard to correct for, and actually can totally screw up the output of your computation. And so you might be hearing this and thinking, oh no, wait, in quantum computing, our quantum states are also sort of analog like this, right? When we're in a superposition, we could imagine doing maybe an RX rotation, and instead of doing an 180-degree rotation, maybe we do a 45-degree rotation. And our computation is super reliant on the fact that we're able to create our block sphere, which is maybe like 45 degrees out. Now you might be thinking, okay, well, if I move to 46 degrees or maybe, I don't know, 36 degrees, that's something that's super hard to detect and super hard to correct for. And intuitively, you would think that is the case. However, there's this whole field of error correction, which, like I said, in digital computing, intuitively, it seems digital classical computing, it seems intuitive to be able to correct, but actually this was a problem that digital computers faced and was only resolved in the 1940s and 50s with the development of information theory by Claude Shannon and the introduction of error detection and correction by Richard Hamming. So Richard Hamming created one of basically the first modern error correcting code, and sort of following him, people found really clever ways of essentially detecting errors in digital systems and then correcting for them. Similarly, actually, a man that you've all heard about before in the context of prime factorization and cracking RSA, Peter Shor, it turns out that he didn't just sort of create this crazy prime factorization algorithm, but he also developed a way of doing quantum error correction known as the Shor code. So like Richard Hamming created a code for error correction in classical computing, Peter Shor created a way for detecting and correcting errors in quantum system. And so while Peter Shor is really sort of regarded in the media for kind of creating hype around quantum computing by showing that quantum computers could be used to sort of destroy modern cryptography, I personally think that his development of quantum error correction is potentially even more foundational, right? Because without this guarantee that you can detect and correct for errors, experimentally, there would be no reason or justification to think that we could actually build functional quantum computers. So this is like a really important fundamental result. And actually, when I talked to Professor Ike Chuang at MIT, he was a grad student at the time that Peter Shor came up with the Shor code. He said that he was out in Stanford and he had the paper faxed to him fresh off the press, and he was just running around Stanford trying to show the results to anyone who would listen, because it was such a big deal for the field that you could actually detect and correct for errors. And now if you try to look into this error correcting literature, you'll see all kinds of really advanced, crazy mathematics dealing with topology and a lot of stuff which is personally above my own head, but it's a really neat and cool field, and people are doing a lot of sort of works. And so quantum error correction, the basic idea is once you can build qubits that are maybe 95% accurate, 99 point something percent accurate, you're basically guaranteed that your quantum computer will work. There's like an error threshold you have to surpass. Then beyond that, it's great. So I have a slide here kind of summarizing everything I just said. Feel free to check it out in the notes later on. But essentially, if you do like the idea of thinking of qubits sort of as dials, you still can. In essence, block sphere, really, you can think of it as kind of like two dials. You have one along the z-axis, kind of controlling your level of superposition. And then you have one along the xy plane, kind of controlling your phase. And remember that phase is really important for creating quantum interference. Now remember, we have sort of three key quantum properties we can leverage in quantum computation, which give us an advantage over classical computation, which are superposition, quantum interference, and entanglement. And so, as we mentioned earlier in today's lecture, entanglement comes about from using 2-qubit quantum gates, specifically the C0, as you'll see in some of your exercises to come. And so with those sort of foundational concepts, we can begin constructing quantum algorithms or quantum circuits, which allow us to do computation which can surpass that we can do with classical computers and the computers we have access to today. So that's all I have prepared for you today. Thanks everyone for tuning in and staying a bit longer, and happy Valentine's Day, everyone.